In this video, we're going to be looking how CDs work. So how exactly does a CD work? Well, the CD is made up of a few parts. We have the bottom. The bottom is made up of about just over 1 millimetre of a polycarbonate plastic. So this is basically like a protection because the information is stored on the layers in between the sandwich. So the next layer that we have is a aluminium coating. This aluminium coating is over the top of the acrylic plastic, which is where the information is stored. The aluminium is used as a reflector. We want our light from our laser to hit the aluminium, turn around and be reflected back to our photoelectric sensor or the photodiode. So we have the polycarbonate base, a sandwich of aluminium and acrylic, and just a bit of plastic on top and the cover and the label and things like that. So how does this work? So I said before that the acrylic plastic is where the information is stored. So the information is stored on tiny bumps. So these bumps make the plastic protrude towards the aluminium layer out a little bit. And this bump is exactly 1/4 of the wavelength of the light that we get from the laser. So if we have light from our laser going through our polycarbonate plastic base, it then hits just a flat piece of the aluminium. It's reflected off and goes back to our photodiode, which is our sensor. So the intensity level of this light is going to be 100% because we have all of the light that's being sent out of the laser being reflected and coming back. Now, if we have a bump, so these bumps are caused from the plastic coming out a little bit, so this is where the information is going to be stored. The way the information is stored here is that whenever the sensor reads that there's a drop in the intensity of the light, we get a binary code coming out of it. So if there is a drop in the intensity, we get a 1. If there's no change, 0. If there's a change, 1. If there's no change, 0. If there's a change, a 1. So we just get a bunch of binary information like this. So if we have a bump and the light from our laser goes up and hits this bump, some of this laser light is actually passing past the bump and hitting the flat surface behind it. That flat surface turns around and gets sent back to the sensor. But remember how I said that this bump was exactly 1/4 of the wavelength of this laser light? If the light that's going past this bump has to travel 1/4 of a wavelength further to then get reflected and travel another 1/4 of a wavelength further than the light that just hit the bump and came back, we have light which is exactly half a wavelength out of phase compared to the light which has hit the bump. If we have a ray of light which is out of phase compared to another ray of light, we're going to get deconstructive interference. Now this deconstructive interference causes the laser light to reduce its intensity because some of it is still reaching the sensor. So it gets a reduction in the intensity, we don't lose all of it. It's not 100% deconstructive. So this change in the intensity of the light is sensed by the photodiode, and this leads to the binary code information, like I said before, being spat out. So how the CD works: a laser gets reflected off the surface of the aluminium coating on the CD. If we have a bump in our CD where we have information that we're going to be changed into a binary code, so the laser hits this bump and it's reflected back. The laser is wider than what the bump is, so we get some of this laser light going past the bump, hitting the aluminium that's 1/4 of a wavelength back, being reflected off that, travels another 1/4 of a wavelength, so it's now half a wavelength out of phase compared to the other light. This reduces the intensity of the laser when it reaches the photodiode. If we just have the flat surface and no bump, we get the full intensity of the light from the laser. So this is how the CD sends its information on. It's a series of bumps. Information on a CD is read from the inside to the outside. So how do we keep our laser on track when this CD is spinning at 500 revolutions a minute? And our bumps are only 1.6 microns apart. We're going to have to use a diffraction grating. So when we look at a diffraction grating, we have, if we have a central beam, we have the first order maximum on either side of this beam. So this is important to keeping our laser on track. So if we have our laser and it shines it through a diffraction grating, we're going to get the central beam and the two first order maxima on either side of that. So this is how we keep our laser on track. So if we have our central beam pointing directly at our bumps and our land, so the flat pieces of space in between the bumps are called land. So we have a bump and we have land. So if we point our central laser directly at the bumps, we're going to have the first order maxima on either side of this pointing slightly in front of it and slightly behind it. So we have our diffraction grating on a bit of an angle. So to find out if the laser is still on track when we're spinning our CD, we look at the intensity of our two lasers from the first order maxima from our diffraction grating. So if the intensity of our two dots, we'll call them, ever drop, that means our laser is no longer on track. This is because these lasers spend all their time on the land in between the bumps. So if our forward facing first order maxima, if that creeps across onto a bump, there's a sensor that records this information, and then the CD reader knows that the laser has gone off track. It then corrects this. If it overcorrects and we have our last laser beam going off into a bump, again the machine knows that something is wrong because there's a drop in the intensity of the laser light. If there's any drop in the intensity of the laser, that means that the central laser has gone off track and the machine needs to adjust the laser to suit. So this is how a diffraction grating is used in reading CDs. If there's ever a drop in the intensity of the light, the CD has gone off track because the leading and the trailing lasers should always have 100% intensity. So the key points from this video today. CDs have little tiny bumps and they have pieces of flat in between these bumps. The bumps are called bumps and the flat is called land. These bumps are about 1.6 microns apart, so they're very, very close together. And we read the information from the inside out. So how do we read the information? We need lasers. So we have a laser that's hitting the bumps. When it hits the bumps, we get some of the light being reflected, and we have some of the laser beam passing past the bump because the laser beam is wider than what the bump is. It gets reflected off the aluminium coating behind it, so it's travelled a quarter of a wavelength to reach that aluminium coating. It then gets reflected off, travels another quarter of a wavelength to make itself half a wavelength out of phase before getting sent back to our photodiode. The photodiode then senses there's a drop in the intensity of the light, and then it changes this into binary code. Binary code is then used by the computer to change it into, say, our music. So, if our laser is travelling on the land, we get 100% intensity. If it's travelling on a bump, we have a reduce in the intensity because of destructive interference. This is because the bumps are a quarter of a wavelength in height. So our reflected beam has to travel half a wavelength. How do we keep our laser on track on the bumps? We use a diffraction grating. A diffraction grating separates our beam into the central beam and the two first order maxima. So the two first order maxima lead and trail the main beam. If any of these leading or trailing laser beams from the diffraction grating gets a drop in their intensity, the system knows that it's gone off track. If it's gone off track, it moves the laser. If it's gone off track in the other direction, and say the trailing beam is now hitting the bumps, we get a reduction in the light coming from the trailing laser, and the machine knows to adjust it in the opposite direction. So the intensity of the two first order maxima should always be 100%. If it's not 100%, it's travelling under bumps, and the system needs to adjust the laser down or up slightly. So this is how a CD player works.